All right, so good morning, everyone. I hope you're doing well. I didn't get much questions from the last tutorial by email, so I guess you are keeping with the rhythm and the speed. Feel free to contact me whenever you need. Last time, I wanted to show you a book and I forgot. So here are the two books. So first of all, the one of last time, it's called Introduction to Polymer Physics, and it is written by Masao Doi. Okay, so Masao Doi is a famous soft matter physicist working in Japan and China. He was working with Sam Edwards and Pierre-Gilles de Gennes in particular on those polymer aspects. And here you really, it's a small book, and you have all the simple statistical description of polymer chains. So I would encourage to do that. It's about the static aspects, the equilibrium aspect. There is no flow, there is no discussion about the dynamics there. And for today, I had another one. So here it is now. It's a more massive one. It's called Polymer Physics from Michael Rubinstein in particular. You can see here, and Ralph Colby from the US. And it's a much thicker one. In fact, this is a very important one where you have all the aspects of polymers, from the statistical description, the dynamics, but also some chemical concepts and developments in the polymer field. So it's really kind of the Bible for this field, and it's quite accessible in contrast to other books that I will show you later on. So please have a look at those or order them if you are interested in polymer physics. And for today, we are going to attack tutorial number 3. It's about refining the picture we gave in the first tutorial about ideal polymer chains. We want now to take into account realistic interactions between the monomers and the solvents. And we would like to see if the statistics is essentially modified and how if it's the case. So please take the tutorial with you on the side, and we will start. So let me share the whiteboard. Up, I hope you can see it. I will move all the annoying stuff on the side. And again, please interrupt me orally whenever you wish. So first of all, I remember that last time there was, during the session, a question about the characteristic function of the problem. So I remind you that we were defining this object as the average of this guy, and it was in the uniform sense. And of course, since the inside of the average is of modulus 1, you were commenting on the fact that, well, that guy should have a norm that is inferior to 1, which is a correct statement. And the problem is that we found that actually, first of all, it was depending only on the norm, not on the vector, but we found something like that, which for values of k larger than 2 leads to problems. However, so we might discuss the mathematical aspects of what happens beyond k equals 2 or minus 2. We could regularize the function in that place or put it to a flat value, thanks to your argument. But other from that, we don't really need to know f of k beyond 0, in fact, because all the interesting points are those ones. If you remember correctly, the derivatives of the characteristic function evaluated at 0 only is the information that will provide you all the moments of the distribution. So the normalization, the first moment, the variance, and so on and so forth. So in fact, despite the comment was correct, we have no problem in the situation we are analyzing, because we only invoked the values near 0. And there is no problem because of the convexity and the minus sign here, okay? So I hope it at least shows that what we did when using this characteristic function was correct. Nevertheless, there is still an open question that I leave to you. All right, so let us start with the present tutorial if there is no more comment. So today we are dealing with refining the previous picture. The previous picture for polymer physics was to have chains that were really allowed to jiggle around and overlap with themselves. We have here an assembly of connected bonds that are allowed to completely overlap with each other. There was no interaction energy, no repulsion, no solvent. It was really an idealized problem for which we were able to demonstrate that the end-to-end here, if this one is the origin, if this one is the final one, reached after n steps, we were demonstrating that the probability of having the vector R in n steps was something that was Gaussian in 3 dimensions. So there was a 3/2 here, and we had that result. All right, so the variance appears, and the Gaussian aspect is here. Right, so we were under those approximations deriving the Gaussian distribution for the polymer statistics of large polymer chains. What we want to do now is to remember several things. First of all, this is bad. In this region, in fact, you have an overlap between 2 monomers. And monomers, they have a typical size, let's say nanometric. They have some electronic clouds around. And so at some point, there will be a strong repulsive barrier. And so overlaps are forbidden in reality. So in fact, what we should have instead is a kind of self-avoiding random walk and not an ideal random walk. We discussed that a bit last time when we talked about the n equal to 0 theorem. That's the first problem. So there is a lack of taking into account the monomer interactions here. There is another problem, is that in reality, this polymer chain is not living in a vacuum like that, but it's surrounded by solvent molecules in a very dense fashion. I will only represent some of them, but in fact, you have solvent everywhere. And possibly, at some point, you will also have other chains nearby that can enter the process, entangle, and so on, okay? So the reality is much more complex. So today we would like to still remain in the description of a dilute solution, so which means that we will not consider the influence of other chains like that. We will only, I will keep those. We will only take the monomer-monomer interaction into account and the monomer-solvent interaction into account and try to modify the picture we have here for the probability. That's the plan of today. So to do that, it's a difficult problem because you have interacting monomers. So it's a problem with nonlinear terms. You have interactions now. It's not an ideal gas anymore. And so we want to have a simplified picture. So the simplified picture would be the following. Is to say that, in fact, the polymer chain has a certain extent. So it can be viewed as a bag in space of size R, where R is the typical size of the polymer chain. So the radius, the end-to-end radius, if you wish. Inside this bag, you have a collection of monomers, and they have all a certain extent A, and their number is n, which is, again, a priori very large. And other from that, you have solvents that are inside the chain in a very dense fashion, but also outside. Okay, you have solvent everywhere, in fact. So this is the picture. And you can take a volume. Here, this is a control volume within your solution, where you have your single chain in green. And we will neglect the connectivity, meaning this stuff. We don't consider that here. We consider we have simply a bag of monomers, and we will do even coarser in description. We will assume at zeroth order that the density of monomers is 0, typically outside the circle, so outside the region where the chain is, and inside the circle it is constant. So we have a uniform distribution, an homogeneous situation. It's the first order approach, okay? Then of course there is a refinement. The polymer chain is denser in the center in monomeric concentration and more dilute on the side. But we will assume that we have simply a zeroth order description, okay? So a bag with a uniform distribution of beds that are the free monomers here, plus solvent. Okay, so in the tutorial, what we would like to do is to, so first of all, place ourselves in any dimension. So the dimension of space is called D. It's not necessarily equal to 3 here. And we will place the system at temperature T, so it's in a solvent, a thermostat, a reservoir of energy with fixed temperature. And what we would like to do is first to provide you the historical, phenomenological or thermodynamical approach proposed by Flory to describe this problem. And then later on in the second part and the third part, we would like to revisit this thermodynamic argument by more statistical physics analysis, in particular the work proposed by Dejean. All right, so here is Flory's model. So let us start. What is the average monomeric concentration in the space pervaded by the chain? So in this little circle, what is the monomeric concentration of the green part? Well, basically, it will be the number of objects divided by the volume of that sphere in d dimensions. Again, here, and it will be through all along the tutorial, I will neglect all numerical prefactors, provided they have no dimension. Okay, we just want to have the scalings here, but you know how to put back any prefactor. Then the question, when we have estimated that concentration, is to estimate the interaction energy. And the simplest proposal would be to have an interaction energy that goes like the square of the concentration. It goes like the square of the number of objects, because you want to count how many pairs you have in your system. So it's n squared that will pop out. So it is pretty clear that if we introduce an energy per unit volume that we call U, it's an energy of interaction per unit volume. Its unit, it's the unit of an energy, and then you have a space length scale to the power D, okay? That's the unit. It's pretty clear that this guy should first go like C squared. Is the minimal description for an interaction. It goes like the square of the field. All right. It is an energy. So there should be an energy scale somewhere. Typically in those polymer problems, the interaction between the monomers are of van der Waals type. Okay, you have a van der Waals interaction between two monomers. There are, of course, in biology some specific interactions that are more related to bonds, like on DNA, for instance. But typically, the interaction will be van der Waals-like. Okay. And the van der Waals scale of energy is comparable to KT in general. So coarsely, and you will see that we can regularize that, people tend to write that the unit of energy is KT-like. Okay, so it's KT times C squared, and we need another ingredient because this is an energy per unit volume. So there is here a volume which is to the square. So we need something, and we put everything we don't control in this guy. And to be more general, since I've assumed that the energy scale is KT and not the typical van der Waals energy, well, I can just put a dependency in temperature here so that I can just put every unknown part in this quantity. And so it's a minimal proposal that contains all the ingredients, right? The important aspect is that V is a volume. So there is a C square dependence, a volume, and a unit of energy in this problem. All right. So now that we have this, let me just rewrite it here on that blackboard. The question is, of course, to evaluate what V is, because we put all the unknown inside V. So let's first look at cases. So when V is bigger than 0, what does it mean? Any idea? It's pretty simple. You have a positive interaction energy, so it's a repulsive situation. I remind you that C is equal to N over RD. So you have this guy squared, V. So you see that if V is positive, you have a repulsive energy. So the idea is that you want R to be as small as possible. sorry, as large as possible, so that this guy in front is as small as possible. So it will tend to extend your chain so that there is no interaction between the monomers, typically. So V positive, it will be a situation that we call a good solvent situation, meaning that the monomers of the chains, they separate from each other and they try to swell, and the polymer chain is really dissolved in the solvent. It's taking a lot of space inside the solvent. If V equals 0, well, then U is equal to 0, and then you end up again in the ideal situation. Gaussian distribution. Of course, now you're killing the interaction again, so we are back to tutorial number 1, okay? And if finally V is negative, well, then this is the opposite. You have a very bad solvent. You have a precipitation, if you want. The chains, they don't like to be swollen. They will, in contrast, collapse completely, and they will stay together, so you will have a solid precipitate in your solvent. So this is the situation where the solvent has been badly chosen, for instance. All right. So now we would like to estimate from this energy per unit volume, we would like to estimate the total internal energy of the chain, of a single chain. So U is an energy, so it will be simply on the scaling level, the integration of that energy within the volume occupied by the chain. Okay, so this is typically KT n squared V divided by RD. So this is the internal energy of the problem. And we are in a canonical ensemble. There is a reservoir with a fixed temperature T outside. So there is also an entropic contribution, and the free energy is provided by the sum of the two. So according to you, what is the entropic contribution here? Any idea? Nobody? Well, this is what we did in the first tutorial, in fact. This is just counting the conformations. So basically, we can assume, and it's a first guess, that we will have something like KT R squared. Remember the elastic term the entropic elastic term that we had last time, which is simply something like that. So the scale of the spring constant was of thermal origin, it was KT, and it was an harmonic oscillator, so R squared. And here, that is the typical extent of a chain in the ideal case. So basically, we can write that the typical free energy of the problem, apart from 3 factors, there is a 1/2 and so on, it's typically KT, and then you have 2 terms. You have the attractive term and the novel term attributed here to the interaction. So it's called V n squared over RD. Okay, so this is the typical free energy of the system in unit of KT. So you have here the entropic contribution that will say what? It will say that you don't really like to be fully extended, because when you're fully extended, you only have one conformation for your macroscopic state, and so it's very unlikely. In contrast, when you are more collapsed, like that, you have plenty of conformation that will allow you to have a typical extent R, okay, in contrast to being completely stretched where you have one single microscopic conformation. So this will tend to, it's a kind of restoring force, yeah, restoring from extension, so it's a spring. Whereas here, you have the interaction term, and when V is positive, it's a repulsive term. When V is positive. So in contrast, this term will tend to, when the chain is put inside the solvent, it will tend to extend and get inside the solvent. So there is a competition between the two, and this is why the statistics or the typical extent might be different. All right, this is a phenomenological approach by Flory. And from that, we can infer the relation between R and nu, the number of monomers. And in particular, try to evaluate if there is a certain exponent. So at equilibrium, the situation that will be observed is a situation that minimizes the thermodynamic potential. So let me just derive the free energy with respect to R. We have KT in front. There is this R squared term, which is here. So you have R over NA squared. I forget all the prefactors again. And here on the second side, you have a derivative of RD. So there is a minus V over RD plus 1. And I should keep the N squared term. And I forget all the prefactors here and here because I'm saying this is equal to 0 and I will balance the two terms. So there won't be any problem despite the strange notation here. All right, so this implies that RD plus 2, if I combine those, will be typically given by V N squared, N cubed, sorry, A squared, by using the above line. And so I can just transform this quantity by normalizing V by A to the power D, so the molecular volume, the monomeric volume, N to the 3 and AD plus 2. So that now if I take the power 1 over D plus 2, I get that R goes like A from this guy, and 3 divided by D plus 2, and a certain term that we will discuss in a minute. All right. So basically, and we will, the topic of the tutorial today will be to discuss in more details that term. But in the Fleury picture, we don't have much information about what is this V. So we cannot say more, but we will do that later. Anyway, we can have the feeling that if the monomers had a 0 size, meaning there were points in the mathematical sense, well, then there won't be any interaction energy. You would have the right to overlap because in fact, there won't be any repulsion between physical points. So in a sense, you could say, and it's a very first estimate, you could say that V is kind of, and be careful with the notation here, it won't be the case exactly, but it's kind of given by the size of one monomer, okay? So in that sense, the excluded volume, we call that the excluded volume of Fleury, is typically the volume of one monomer. And therefore, this term, you could say that at first sight is something which is of order unity, doesn't evolve much. So in a sense, you are left with something like that, which is interesting because it resembles what we had last time. R goes like A monomeric size to the power N to the power nu. And with nu being equal to this guy. So sorry, I just erased the previous whiteboard. So I recall it here. Okay, so it's exactly what we had last time, apart from the fact that now that nu is a function that depends on the dimension of space first, and that is not necessarily equal to 1/2. Okay, but there is a scaling law, pretty much like in the ideal case, and we can have a look at nu. So let's take the case where we are in dimension 1, for instance. In dimension 1, nu is equal to 3 over 3, which is 1. So it means R goes like N. Any comment on that? Is it expected or not?
Yes, it is.
Yes.
Yes. Why?
Because we have a repulsive interaction between the monomers.
Correct. And now we are living in a 1D world in a tube. So if I place one monomer on one side, well, the next monomer is either here or here, but as soon as I've positioned here, the third one cannot come back. So it's there. And then there, and then there. So in fact, it's really a ballistic motion. It's not anymore diffusive. And this is due to the fact that there is a wall, a forbidden barrier. Okay, so nice. D equal to Well, you have an exponent which is 3/4, which is bigger than 1/2, okay? Despite the fact that in 2 dimensions, a random walk is also given by a 1/2 exponent. So really here, the repulsion interaction is making the chain a bit more swollen. D equal 3 is the case of interest in our typical world. And there we have something which is 3/5. So it's equal to 0.6. So again, it's larger than 1/2, slightly larger. You could say that it is really meaningless in terms of, let's say, measurements, but it is not. You have to remember that you are in the limit where n is much larger than 1, and therefore at some point it will be much larger in terms of total extent of the macromolecule if you have interactions that repel the monomers than if you have not. And this tiny difference in the exponent is in fact meaningful at the thermodynamic limit for infinite number of monomers. Finally, there is an interesting point, and I could go on with the list, but there is an interesting point, which is the following. You have this guy, so it's 1/2. So there is a certain dimension at which the exponent becomes strictly 1/2, as if there was no interaction, okay? Apparently, despite you're putting a non-zero V. V is non-zero, so the excluded volume interaction is non-zero. Any comment on that? Does it ring a bell? Does it remind you of something else? No. So for critical phenomena in stat phys, this is what we call the critical dimension of space, for which the interactions are meaningless. So if you have a problem with interactions in the real world, and if you increase the dimensionality of space, in a sense, by having more direction in your space, the interaction will be less annoying. You know, they are very annoying in 1D, as you can see here. They are forcing you to be completely ballistic in our case. And as you increase the dimensions, in fact, the interactions are not less critical because you have other ways to counteract the problem in a sense. And in stat phys, there is this notion of critical dimension for which you can really make the system ideal in the sense that there is no more interaction. Okay? And this is a strong connection. So it says that there is a certain dimension, which is 4 in our case, for which basically the interactions do not matter. And this is why in some renormalization group theory approaches, or in some critical phenomena approaches, people are increasing the dimensionality of space to 4 or to the critical dimension. Do some calculations there because it's an ideal problem without interaction, so you can calculate everything, and then just do a Taylor expansion on the dimensionality to go back towards the 3 dimension that we know in a typical world. So we will discuss that during the next tutorial, but you have a feeling that there is some special dimension in this problem. Okay? All right. So now we are wanting to revisit that Flory approach, but in a more statistical way, where we'll really try to evaluate what are the probabilities of the conformations we have in details. Okay? So let us first remember exactly what was the problem in 3D. So when D equals 3, in the case where there is no interaction, okay, so U is equal to 0, the internal energy, we had a probability of getting a typical extent, R, in n steps, that was provided by the solution of a diffusive equation. So it's the Green's function of the diffusion. So you had here 3/2, so it's in 3D. And there you have this quantity with again a 2. And there should be a pi here due to the integral of a Gaussian. This was the result of solving the diffusion equation on P with a certain diffusive coefficient, which was a²/6, and then you have your Laplacian of P. Okay, so the solution of that, starting from a Dirac, this is the Green's solution, is this one. This is in 3D. And let me just stress the fact that this a²/6 that appears here was in fact 1/2 remember we did a Taylor expansion within the Markovian identity. And we went to the second order. So when you do Taylor expansion at order 2, there is a 1/2. So it was 1/2 times 1/3 times a squared. And this 3 here was the fact that we were estimating what is the average of R squared, R being the length of one monomer. And it was 3 times x squared, for instance, because all the directions of space are equivalent in a free diffusive problem. So that is why we got those results here. So this, just to say that this tree is in fact D, the dimension. And similarly, you have here the normalization. And for each directions of space, you were normalizing the Gaussian. So this tree is also a D, in fact. If you go to the dimension, this one we already discussed it. And this one is in fact reflected in the variance, so same here. So we can, without any calculation, simply say that the probability of having a certain extent vector after n steps when n is large in a dimension of space which is D, well, is simply D over 2 pi NA squared to the power D over 2. And then there is this R squared 2 no pi here NA squared. And up. Okay, so without any calculations, you believe me that the problem is still Gaussian. Diffusion problem is always the same in each direction. You just have little corrections thanks to the new dimension here. Okay, no problem with that, I guess. All right, so from that, P of R and N, if I integrate it, or if I take the element of probability in a D dimension world, so this is P of R and N. Here you have R D minus 1, dr, and d omega. And d omega is the element of solid angle in a D dimension space. So in 3D, this would be the usual d theta, d phi, sine theta. Okay, but here it's more complex, and the integral of that is related to gamma functions. Okay, but basically what is important is that you have the dimension of space minus 1, R, dr, and then purely angular considerations. The second important aspect is that, in fact, this guy doesn't depend on the vector R, but only on the norm. So if I recall the expression above, I end up with D over 2. Then I have this R D minus 1, exponential minus D R squared without the vector. And everything being integrated or with the element. Sorry, I'm just doing the element here, no integration yet. Okay, so you agree with me that this is the elementary probability of getting the vector R in n steps, provided that it's the vector R plus a small variation, so within this little volume. And so now what I see is that there is no dependency in the vector anywhere or in the angles anywhere. I have only the norm that appears here. So I can integrate that quantity over the solid angle. And this will give me, so if I do that, I take P of R n R d minus 1 dr d omega, and I integrate over the solid angle only. Okay, and so this, apart from prefactors, will give me something which is R d minus 1. I don't consider also this guy. I don't care, because in this guy, you don't really have R dependencies. So I will also forget this quantity, because you saw just before we were deriving the free energy with respect to R. So R will be our variable. So if there is no R, for me, it's not really meaningful. But you can keep all the prefactors I told you, and just make sure that you agree with what I say. So now we end up with a function which is the following: 1, 2, and a squared. And that's it. And here there is this d of R. So I will call that P0. It's the probability of having a certain extent R, okay? Provided that I have instead. Okay, so P0 is my central quantity in this the 0 means ideal. It's typically depending on R this way. All right. So now we have recalled the ideal situation. The limitations, you remember them. To describe this, there is no contact between the points that is forbidden, and also there is no solvent. So it's a kind of idealized problem. Thus the Gaussian shape. All right, so now we have a certain distribution, and so we could try to look at some equilibrium properties. So what should we do? If we want to estimate the typical relation between R and N, do you have an idea? I'm interested in that guy. Is there any scaling law between the size of the chain and the number of objects therein? Well, let us maximize the probability. It's equivalent to minimizing the potential in a sense. Okay, the thermodynamic potential appears inside the exponential. So when you say that at equilibrium you minimize the potential, in fact you are maximizing the probability, something like, right? If you have a probability that goes like beta times the thermodynamic potential, maximizing the probability, so the most probable state, if you want, is equivalent to minimizing the thermodynamic potential. So let us maximize the probability. And I won't check that it is a maximum, you can do that easily. So let me derive the probability with respect to R. So what do I get? Well, now I have two terms. So I have d minus 1, I don't care about the prefactors. So R d minus 2 times this exponential. And there is another term. And then I should derive this exponential with respect to R. So there is a minus 2d over 2n squared R, and then exponential minus d r squared over 2n squared. And this should be equal to 0. And again, I say that I don't care about prefactors because I already removed a lot of those. So I will even remove the d, the dimension, which is numerical. All right, so in terms of scalings, what do I get? There is a minus sign, so I can just put that term on the other side of the equality. I can remove this guy. And then I end up with R d minus 2, which scales like RD divided by NA squared. So this is equivalent in saying that R2, okay, goes like NA squared, or stated differently, that R goes like the square root of N and A, which is nu equal 1/2. This is the diffusive behavior that we discussed extensively in the first tutorial. So it's obvious, we were just extending to d dimension the probability that we uncovered in the first tutorial. So we just extrapolated to d dimension, but the relationship is still diffusive. And so the typical extent, there is no interaction here. The typical extent is this one. Okay, so let me just come back here. All right. Okay, so this is the reference state. Now we would like to understand the effect of interactions. So our strategy here is the following. We have plenty of conformation, okay, of chains. Some are overlapping, some are strongly overlapping, and some are really fully extended. They are very rare, but they exist in the statistical ensemble. And so the idea would be first to rely on the ideal description and compute all of them. So we know the statistical ensemble of the Gaussian problem or the ideal situation. And from those, we will, each time there is at least one crosslink or one crossing point, I should say, we will just remove it, forbidden, one forbidden. And so the idea is to try to do a kind of corrective or perturbative approach to the ideal situation, we have this picture with plenty of conformations and some energy and entropy, if you say, energy being 0, that you have an elastic term coming from entropy. And from all those conformations, we will remove all of those who have at least one crossing point. So the question amounts to evaluating the number of those conformations. Okay, and this is what we want to do now. All right. So remember, the problem has been simplified at 0th order into a bag of extent R, which is the space occupied by the chain, and populated by a certain number of monomers. Each of those having a size small a. And you have a very large assembly of such monomers. First of all, here we are not considering any solvent. We really have hard spheres like that in a bag, and we don't consider any interaction due to the solvent. The question we want to answer is the probability for two given monomers. Let's say this guy, number 1, and this guy, number 30. We want to know what is the probability that they occupy the same space, that they touch physically. So remember, we are in a uniform description. That is a simplification of what is really going on. Do you have an idea of what is this probability? So it's the probability of overlapping for two given monomers. Any proposal?
Well, maybe that would be the volume of one monomer divided by the total volume.
That is correct. So basically, we have a certain volume, RD, and we want to fix the first monomer. Let's take this one, for instance. So we have one monomer. What is the probability of the other monomer to touch? Well, it has plenty of positions allowed, except one, which is the one of the first monomer. So we just do the ratio of the two volumes. It's uniform, so it's just proportional to the volume, in fact. Correct. So that's the probability for two given monomers. However, there are plenty of possible pairs, and so we want to estimate the number of pairs. So what is the number of pairs? It's a trivial question. Total number of pairs. I have an assembly of n objects. How many possible pairs do I have?
n minus 1.
Exactly. Is it strictly that? Is there anything else? Am I not overestimating the number of pairs? Because choosing the first one, n possibility, then I need to choose the second one, of course, n minus 1 possibility. But if I've started with this one, and then the second one being this one, it's the same pair. So I'm counting twice, okay? So there is a factor 1/2. Agreed?
Mm-hmm.
Okay, and so at large n values, this is typically n squared over 2. So this is the total number of pairs. For a given pair, I know the probability P. Now I can compute what is the probability. Remember here, we wanted to evaluate the conformations where there is at least one touching. So we want to only keep the conformation for which there is no touching between monomers. So now the stuff we want to do is, sorry, this was number 4, I guess. We want to study the probability of two monomers not touching each other. So if P is the probability of two monomers specified to touch each other in space, well then we will introduce Q, which is simply 1 minus P, which is the proba of no contact between two given monomers. Okay? And now the probability that I have a conformation that has 0 self-contact, what it is, I call it pi. What is the probability of pulling randomly a conformation, but with a conformation that has strictly no contact between monomers?
Q to the power of n squared over 2.
Correct. All right, so this is simply this 1 minus a over r to the power d to the power n squared over 2. Okay, so I know now, remember, I want to factorize the two problems, assuming they are kind of independent. This is only true as a perturbative approach. I'm first describing the system as ideal, so I have all the possible conformations. And among those, I want to calculate the probability of the conformations not to have any crosslink. And this is the ones I would like to keep at the end. So I will kind of factorize the two approaches, okay? Assuming there is an independence between the two, which is not strict when the interactions are strong. All right, so remember we are at large n, and therefore I can just expand that guy. So pi is something like the exponential of n squared over 2 log of 1 minus a r over d. And at this limit of very large number of monomers, the size of the chain is growing a lot. And so it is pretty clear that this term is small. So I will keep only the dominant term, AD over RD. Okay, so I'm consistent in the sense that I'm here now for the interaction part, taking into account also a large number of objects. Be careful. It's not because I have an equivalent of the logarithm here that I know that the exponential of that equivalent is straightforward. You have to make sure that the rest in this Taylor expansion tends to 0 for having equivalence for exponentials. So you can make sure of that by, in R here, you put the Flory proposal that we described at the beginning. You estimate the new exponent here for R, and you make sure that the term you've neglected here in this Taylor expansion tends to 0, so that you have a proper equivalent. The response is that it will be working correctly. Only this term matters, but please do that as a homework. Make sure that you understand everything. All right, so now we have pi. And the question I would like to ask now is the main one. What is the probability of having a certain extent R in n steps, but now under the presence of this constraint that I cannot overlap? The chain overlapping like that is forbidden. Okay, so can you tell me the result based on P0 and pi? What is your guess?
P0 times pi.
Yes. Again, this is an assumption, but it is a reasonable one. If the interaction is vanishing, meaning that it's very rare that you have a strong repulsion here, you can assume that you factorize the two problems, saying that counting all the conformations and then removing the parts where you have interactions are two separate problems. In fact, the interaction is affecting the probability of conformation, so there is a coupling term between the two, and you cannot really factorize the two probabilities. But in the limit where the interaction field goes to 0, this is the zeroth order guess. Okay, so that's what I want to do, and I want to say then, since I know P0, it's typically, I already know the result. It's minus R squared with dimension D 2NA squared, and then pi. Now I just calculated pi. It's here, so it's provided by a term in minus NA squared. Minus n squared over 2, and so it's not a squared, but it's a to the d, r to the d. Okay, so this is my P1. The one here refers to the fact that it's the correction with respect to P0, P0 being the ideal case. So now I have added a term, a factor, that makes sure that there is no interaction, no self-crossing point. Okay, and this is the Gaussian part that we already know. Is it clear? Or is it not clear, I should ask. Okay. All right, so now we will follow exactly the same trend as before. We want to estimate what is the minimum of the free energy. And so we want to find the maximum of probability here. So what is the maximum of the probability? It's obtained when this guy is equal to 0. And dr of P1 is, let me now compute it. You have 3 terms. You have r d minus 2 times the exponentials. Okay. Now I have another term which is coming from the derivative of that quantity. So I keep the prefactor d minus 1 that was present here. And I just have this minus, so I forget the prefactors. I have minus r over n squared. And then I keep the 2 exponentials. Okay, and then I have a third term, which is coming from the derivative of this quantity. So the prefactor that will jump out is minus r over d will give you plus y over r over d plus 1. And then I have n squared ad. And again, the 2 exponentials. In a minute, I will stop writing the exponentials because they will anyway factor out. And you could reasonably argue that, well, I'm writing a scaling symbol all the time, but now I have more than 2 terms. So I don't really have the right to just sum things without putting the proper prefactors. And this is completely valid. The thing is that in a minute, we will see that only 2 terms are dominant in this sum. And so I'm still self-consistent. But please put all the prefactors if you want to do that carefully. Okay? All right, so I will now just remove the common prefactor here that is strictly positive. And I end up with a list of 3 terms. So I have r d minus 2. I will put that on the other side. So I will keep this one. 1 over r2. So n squared ad over r2. And then I have AD, and then I have on the other side this quantity, which is R D over N squared. This is what I get. And this guy, I can rewrite it such as times R2 over N squared. It's equivalent. Why it is interesting? Well, now I have 2 terms that resemble each other. I have this guy and this guy. And so I can compare them. So in your opinion, I'm dealing with now a situation of good solvent with a positive V. What is the dominant one at large N? No guess? So we are in a, you can think about the Flory picture we had before. For dimensions between, let's say, 1 and 3, or 1 and 4, strictly inferior to 4, this goes like that. With a nu that is typically bigger than 1/2. Meaning that we have a chain which is generally much more swollen than the ideal situation. Therefore, this factor here is much bigger than 1 rapidly. So this quantity is larger than this one, and we can rapidly forget that term, okay? So it says that, in fact, I have only to balance these two terms. So I have RD over NA squared. That scales like the other one, which is this one, N squared AD. Over RD, R squared or RD? R squared. And this is equivalent to saying that I have the following relation. Similarly, I could take the power 1 over d plus 2 with a certain exponent a, and with nu, which is equal to all right. So any comment? What do we get?
It's the same.
Is the same as what? I know you know the answer, but for everyone. Is the same at? Is the same that?
So do we answer? Or?
Yes.
Okay.
Yes.
Yeah, as the Flory model.
Yeah, so it's almost the Flory model. You're right. We recover the Flory model, but in one specific case. Let me just scroll back so that we see the Flory. Here is Flory, right? So yes, we have A, the monomeric size. You have the number of objects to the power nu with the same nu, and there is this term that is now missing in our case, right? So it seems that V is simply equal to AD. So it's the Flory model with a specific value for the excluded volume, that is AD. Let me just just keep this symbol that I like. Okay. So in a sense, what we did when we avoided any self-connection in the random walk, so really we were shooting for random walks in a sense, and each time there was an overlap, we rejected the walk, so that we left only the self-avoiding random walks. By doing that, we get the proper exponent proposed by Flory in his phenomenological approach, and we get another thing is that we have now a physical intuition on what is the excluded volume, what is the parameter in the energy of Flory. And now we say that, well, it's typically the size of a monomer. If that size goes to 0, there is no more interaction. Remember that the interaction of Flory per unit volume was something like kT, scale of energy. C squared, it's an interaction, so you had the power 2 of the field, of the concentration. And then there was this important unknown parameter in Flory's approach. He was a chemist. He was just saying, well, there should be something with the unit of a volume that should characterize kind of the interaction. So a volume characterizing the interaction between monomers. Well, now we have a pretty clear picture. It's the volume of the monomers. Okay, so it's interesting. So we recover a bit more quantitatively what Flory had in mind, but we made some course description. I remind you that we were assuming that the chain is in fact an assembly of independent monomers in a bag. And there is a uniform distribution of those beds. And we were just, so that's the first picture, it's not correct. And the second part is here. When we factorize the two, well, we don't have the right to factorize the two because the fact that there are repulsion between monomers will in fact affect the statistics of the configurations. And so therefore it's not clear that we can just take P0, the ideal version, and reject the bad conformation. So there is a kind of perturbative theory behind. Anyway, we have a start to get a correct understanding of what is going on. And I told you that in Flory's picture, the solvent was a key element. In a sense, we were saying that, well, the chain will start to swell a good solvent. So when V is positive, we said it's a good solvent, in the sense that the polymer chain likes the solvent, and so it wants to extend in the solvent and take as much space as possible. But in fact, here there is no solvent. So you see, we get the swelling ingredient just by avoiding repulsion, and this is the idea. In fact, as soon as you avoid contact between monomers, well, you have a more swollen chain. So a self-avoiding random walk is larger in extent than an ideal. No solvent here. But of course, in reality, there is solvent. And this is what we would like to consider now. Do we have any questions on what we did so far? No? So let me just comment before we go to the next point briefly on the fact that you can take your favorite Python or MATLAB or Mathematica software, and then you can take a lattice in any dimension of space you want, and then you can shoot for a random walk. So you take a starting point, and then you decide where will be the next point on the specific lattice you've decided to prepare. And then same, the third one and the fourth one. And so you create some random walks, plenty of them if you want. It goes very fast if you do it yourself, you will see. And then you can say, well, now I had a constraint. If the site is already occupied, I cannot go there. So I'm really doing the simulation of a self-avoiding random walk on a lattice. And then you can do statistics, plenty of conformations, and try to estimate from the ensemble the typical extent. And what you will see is that you get with new, which is, if you are quite precise, this is typically what people can get, and you can have more figures in the row. So it's kind of close to 3/5. I'm talking about 3D, sorry, for those simulations. You would get other results in 2 dimensions, of course. Remember, this is 0.6. So in fact, what does it say? It says that the Flory approach and the simplification in the statistical description we made are not exactly resolution of a self-avoiding problems. We made some approximations. Okay, that is why in our case, we get a strictly 0.6 exponent, and in reality, with very fine computing, and it has been published in several articles, well, in fact, it's slightly smaller than 0.6. And this is exact. I mean, in the sense that you can trust that. So it's not true that you have a 0.6 exponent in reality. In fact, we call that self-avoiding random walks. This is the short nickname for that. And it's an open field in mathematics. People are trying to get some asymptotic results for this particular type of Brownian motion with some memory effect. And so it's an open question, okay? So you can have a look at that if you are interested in mathematics. Anyway, we are doing pretty well with a very simplified picture. All right, now remember chemistry a bit. That chain doesn't live in empty space. There is a solvent around. So we now complexify the picture again. We have this bag, certain size R. We have monomers. First, we shoot them in an ideal fashion. Then now we branch repulsive interaction between them. This is what we made. So they cannot overlap. They cannot be at the same position. And now we add the fact that you have solvent as well. We assume that the solvent is made of spheres with the same size, typically A, as the monomers. And of course, you can have solvent outside the chain. Okay? So this is now the typical picture. And we want to do exactly the same logics. First, we have the ideal description. Then we correct that description to take into account the avoiding of contact points. And now, third ingredient, we branch some interactions between guys. So those guys that talk to each other. but also even if they don't have the same color, they talk to each other, right? And same, we already knew that those guys talk to each other in the sense that they have a repulsion part, but on the long range, they will have an attractive part, an attractive interaction energy. This can be summarized for any pairs by typically the Lennard-Jones potential. You have an interaction energy. You have a typical spacing between molecules, and you know that from van der Waals like attractive potentials, any condensed matter material is cohesive. In the liquid state, you will have interactions that tend molecule to assemble to form a cohesive state of matter. So this is the attractive part of the potential, 1/R6 dependency typically. And then if you go too short, then you will pay another price, which is like now your clouds of electrons are starting to fill each other, and then even more electrostatic contributions from the inside of the nucleus. So you have a big barrier here that forbids contact. In fact, so far we were actually focusing only on that part. In P1, we already had the fact that two monomers could not overlap. So we already took this repulsion into account, but now there is this attraction at long term that we would like to incorporate. We can describe any of such potential by a typical energy. This is a cohesive energy, and we call that alpha beta. So alpha and beta, they can belong to either P for polymer or monomer, or S for solvent. You have two species in our problem. So you have three energies that are important: EPP, EPS, and ESS. Okay, epsilon. So I have two species, so I have three possible interactions, and I need now to incorporate those enthalpic or energetic considerations into the previous problem. And so you understood the idea. We now would like to calculate P2 as P1 times a new probability that we want to compute, P, which takes into account how much favorable is one conformation with respect to another, viewing the van der Waals interactions. Okay, that's the goal. Any question on that before we start? Nope. All right. So first, some considerations about the dimensionality of space and the typical number of neighbors. So if I am in a 1D world, it will resemble, the continuous world will resemble a lattice like that. And each point of this lattice can be occupied either by P object or by S object, solvent molecule or monomeric molecule. And typically, if I consider one vertex here, well, I have two neighbors, this guy and this guy. Okay, so the typical number of neighbors that I called Z is here equal to 2. If I go to, this is D equal 1. If I go to D equal 2 in 2 dimensions, let's assume I have a lattice which is square. Now, the typical number of sites around myself is 4. Similarly, in 3D, I will get that Z is equal to 6, because I would now add those two guys, and so on and so forth. So if I consider a cubic lattice, the typical number of neighbors of any site of this lattice is 2 times the dimension. Of course, the continuous world, like a solvent, you are in your laboratory, you are preparing your polymer chains, synthesizing them and putting them in solution. Well, of course, it's not a lattice discrete with a cubic conformation. So it might be that this number is larger than 2D, okay? Especially in a dense solvent. Nevertheless, it gives you an idea that this grows linearly with the dimension. Okay? So this is the typical number of in the bag. If I take a specific site, this site can be occupied either by a solvent molecule now, or a monomer. And this site is surrounded by a certain number of other sites. And the question will be, well, are those sites occupied by a solvent molecule themselves or a monomer of the chain? And then you'd have different energies to take into account depending on what is occupying that neighboring position. Okay, and we will count the number of conformation for each case. Right? Then put a price for it, an energy price, and then go to a Boltzmann-like factor to penalize strong energies. So this guy will be typically a Boltzmann factor. Okay, and then we will expand our total probability and again try to find what is the typical relation between the radius of your polymer chain and the number of objects. So I hope the program is clear. So let us now try to estimate within your space pervaded by the chain, what is the typical volume fraction occupied by the chains, by the monomers of the chain. So the typical volume fraction is the number of objects, the volume of individual monomers divided by the total volume of space. Okay, so this is the fraction for the P species, meaning the monomers. Okay, so then we would like to calculate what we call N alpha and beta. It's the number of pairs on average for each type. So NPP here is the number of pairs of neighbors where you have one monomer on one side of the pair and again a monomer on the other side. So really you have your bag here, you take a site and one of its neighboring sites is occupied by a monomer. So you have two monomers that touch themselves. All right, so what is the typical number of such configurations according to you?
N.
Yes. That's a good starting point. What else? So N, what you have in mind probably is when I have my polymer chain here, I have N possible monomers. So for a pair, I should first choose one monomer. So this is the first point. So I choose one of them, this one. Okay, now this one has a certain number of available sites around it that is provided by Z. So let's now count the number of possible neighboring positions. I have Z of those. Okay, now for each of those neighboring positions, say this one, I need to make sure that I have a polymer, a P entity, not a S entity. So what is the probability? Phi. And am I done with that?
Divided by 2.
Yes, that's correct. Again, because I don't want to double count. Okay, straightforward. That's NPP. So now if you understand the logic, let me count NPS. Exactly the same drawing, but here I would just ask for a solvent molecule to be there. Okay. So can you repeat the process? Again, since it's NPS, there is P inside. So first I need to have an object belonging to the chain. So I need to decide which one. So it's pretty clear that your previous intuition still works. It should be linear with N, okay? At least for the beginning, okay? So I should first choose what is the starting point. This guy. N possibilities, okay? Then, how many names? Yes?
Z1 minus phi.
Yes? No factor 1/2 here, because I have no double counting since I have only one of each. Okay? Perfect. It's correct. Now I want to evaluate NSS, which is the remaining one. So let me remind you the picture that was shown here. In fact, I have a control volume, a box, which is full of solvent. It's really dense. It's a liquid, so there is no vacuum in that description. I mean, all the sides of the lattice are occupied. But in a sub-part of it, of size R, there are now two species, N black points, and the rest being occupied by red. So in this green box, this control box, or if you want, it can be the full solution if I have only one chain in it. Well, the total number of sides of the lattice is fixed. Okay, it's related to the fact that we have a dense material of density 1. Okay, all sides are occupied. So if I come back here, I can just, sorry, let me go to the correct here. I can instead express the conservation of matter, the total number of objects, thanks to the previous drawing, is equal to NPP, so the total number of pairs, NPS, plus NSS. And this is conserved. It's a finite number. Therefore, I don't really need to calculate this quantity because it's a constant. And you will see that it doesn't matter in a minute, but for now, I can just keep it as a constant. Minus the two things we already calculated. So it says that NSS is equal to a constant minus the two above. All right. So in a sense, I have identified on average, of course, this is an average. You can see that through, in particular, the volume fraction that is in a uniform sense. This is the probability. We have characterized all the possible numbers of pairs on average. So it means that we can have the average energy in a sense of a certain configuration. And this is what we will do now. And so we will remember that the energy, the total energy, I call it E, well, is simply the sum of the energies for each individual bonds times their number. So it's sum over all possible alpha and betas, but counted once only. I don't want to have PS and then SP. It's the same number. N alpha beta, the number of such pairs, times their energy. And their energy, it's a cohesive energy, so it's minus epsilon alpha beta, which could be seen here. The norm is epsilon alpha beta, but it's a minus sign because I want to have a cohesion. Right? So in my language, it's simply NPP times epsilon PP NPS epsilon SP or PS and NSS epsilon SS. Okay, and now I know everything because I already computed those guys. So I will replace the values. So NPP is NZ phi over 2. So I have NZ phi over 2 times epsilon PP. That's the first term. NPS is NZ1 minus phi. And I pay this price. In fact, now I have NSS, which is N tot minus NPP minus NPS. Sorry, NSP. NPP, NPS. Okay. Okay, and I should have replaced those guys by their values. So this is NZ phi over 2. And this is NZ 1 minus phi. So let me expand this so that we have all the contributions and we can think about them in closer detail. I will really expand all the sums. This constant term. Sorry for the handwriting on the tablet. All right, this is it. This is my total energy, average, knowing the typical average number of each conformation and their energy price. Okay, so in those terms, I'm considering the one where there is a R dependency. And the R dependency is in fact in phi, because phi, I remind you that it is NAD, so the volume occupied by all the monomers divided by the volume occupied, pervaded by the chain. So the dependencies, they are here, they are here, they are here, they are here. The rest, N, Z, connectivity of the network, energy, those are constants with respect to R. So when I will be deriving my probability or my thermodynamic potential with respect to R, those won't contribute. They will factorize out. You can keep them if you wish and check that I'm correct, okay? But since we already went through this question, things are pretty clear. So I can write this as minus NZ phi, keep only those relevant terms, in front of what? I have epsilon pp over 2. I have minus, plus epsilon sp. I have this one, which is, no, sorry, it should be a minus here. Up. Okay. Then I have a plus, which is here. I have plus ESS over 2. And the final one is, no, sorry, again, it's a minus. I'm tired today. All right. Then plus NZ phi epsilon SS. All right. Did I miss something here? No, it seems correct. Okay. Plus constant term with respect to R. All the remaining term, I can put them here. And as I told you, I won't change notation. I would just simply ignore them. I should have changed the name of the energy, but I would still keep that part named as E. Oops, sorry. Where am I? Here. Perfect. So the total energy for my problem can be written as minus NZ phi with some quantity that I can define as epsilon pp over 2 plus epsilon ss over 2. So if you want something like that. And then there is a minus related to epsilon sp. So it's a much more compact form for the energy. And this, I could also put the half in front. So it's epsilon pp plus epsilon ss minus 2 epsilon sp. So can you comment on the physical meaning of that delta epsilon? Any idea? Let's assume that this is the final state and this is the initial state. What does it mean?
this means that the particles will, the monomers will go with monomers and the solvent will go with solvent. So there is like a precipitation.
Yes, we could like we call that segregation. In fact, this is exactly that. So the starting point is 2sp. So let's say you have S and P that are nearby. So you have those two bonds somewhere in the bag. And then after the transformation, you get a segregation where similar objects self-assemble, okay? So it's really a segregation. And so this is the difference of energy between the two configurations, so from the initial state to the final one. So this is, if you want the gain, remember that there is a minus sign in the epsilons. So it's a gain of energy thanks to segregation. What it says, it's typical for van der Waals interactions. The best neighbor is someone which is very similar to yourself. It's a very sad statement, but it says that typically if you put two entities in a box and that you don't have any specific temperature, let's say the temperature is small, then the quantities, if they are obeying some van der Waals-like interaction, they will tend to regroup themselves with the people who resemble them the most. So you can have ghettoization if you want. So it's a very sad process. And of course, the idea to destroy that is to inject energy from outside. And KT is the key. Now, if you put KT, well, you will force mixing. Like in politics, if you want to kill the natural segregation between people or classes of the society, you have to inject energy, political energy or economical energy. That's the only way. Otherwise, you will tend to go towards self-assembly with similar entities. All right, so this is the essence of delta epsilon. And now we have the energy here, so we can really go to the Boltzmann factor. And we can, and this is the next step, calculate P2, I guess. So P2 is the probability of first having some configuration that is shot through the ideal random walk description, then forbid any crossing point, so the repulsive barrier of interactions between monomers, and then now, well, put a weight thanks to all the interactions that are attractive between monomers and monomers, solvent and solvent, and monomers and solvent. And so now we correct that guy with the Boltzmann factor. And now I have really a probability feature that has all the ingredients inside. The anthropic one of plenty of conformations, the repulsive one thanks to the hardcore repulsive barriers, and then all the interactions with solvent or not, and we have averaged it inside E. So this could be rewritten as what we already did times that guy. Okay, so let's remember what is P1. P1 was like P0, so there is this RD minus 1. There is the Gaussian of the random walk. And there was the cohesive term, the interaction term, and it was going with the number of pairs, so n squared over 2. And there was this A over R to the power D factor. So this is P1. Now I want to add exponential minus beta E. So E being this guy, NZ phi delta epsilon. There is a plus now, times beta, or if you prefer, divided by KT. Okay? And I don't care about this symbol. All right. Is it clear for everyone? Okay, so I can just reformulate it by really precising all the R dependencies. Okay, as before, and this one I can specify everything. So I have n squared, because in phi there is a n, z, ad, delta epsilon, sorry, it's an epsilon here. I will correct that in a minute. And RD KT. And this guy is an epsilon as well. All right. So it starts to be a long expression, but basically I have entropy, elastic repulsion between monomers, and then I have attractive interactions. Interestingly, the interaction even between two entities that are not the same, so solvent and monomers, they are attractive. But the reason why there is segregation is that they are less attractive than similar entities, okay? That is why there is segregation. So there's still a hope. All right. So now we would like to make a remark about that. Can you do that? Can you look at this specific term here in closer detail? And try to connect it to this one. Don't you think that they resemble each other in a sense? You have this guy, you have this guy. And then there is a dimensionless quantity, which is a kind of ratio of energies, interaction energies over KT, so the amount of the two energies in the problem balanced. So by a writing trick, you could simply put them all into the same exponential in a sense, with the same kind of dependencies. So let me do that now. P2 is in fact, should use a scaling symbol here, but anyway, well, let me do it everywhere so that you are not confused. Of course, we forgot plenty of prefactors here. Even in terms of dimension, this doesn't work. So what do we have? And then I will group everything in the following way. And I will keep AD. Okay, so I have what? I have AD. So this is 1. And here I have -1 because there is a minus. And I have 2z delta epsilon over kBt. Okay, just by playing with the writing. So I could again rewrite everything in a compact form. And I will change the name of that guy and call it V without too much surprise. And I will define V in a minute, but I can just group all that stuff into a kind of renormalized volume, which is not AD anymore. And I end up with V, which is equal to A to the power D, 1 minus 2 something. So let me call that something psi, psi being the ratio of the typical energy of interaction. Remember, there is connectivity also because I need to know how many times this arrives in unit of thermal temperature, thermal energy, sorry. We call that the Flory parameter, by the way. You will see why in a minute. Okay, so it seems that, in fact, the repulsion part, monomers together, they don't like each other because they are too close. So when they are really on top of each other, they don't like that. So this repulsion tends to make the chain swell a bit. And here we are saying that in fact, the solvent term, which is this one includes solvent, has the same shape. And so it's basically going into the same kind of picture. So it will also control the swelling of the chain. So we are saying simply that now the interaction Flory parameter, the excluded volume small v, is not anymore simply the volume of a monomer, but there is a renormalization of it thanks to the interactions. Okay? And so now we recover Flory's picture. All right. Now let's take van der Waals interactions. So van der Waals interactions, what matters in the, you remember the energy of interaction is cohesive, so it's minus. There is a constant, and this constant depends on plenty of things like h bar if you have some quantum effect, on speed of light if you have some retardation effect of the interactions. It depends on kT. Sometimes you also have to average. You have several dipoles, electric dipoles that are fluctuating, and you want to average on all the angular position. But basically, whatever is the origin of your fluctuations or your transmission of the signal, you end up with an interaction energy for van der Waals interactions, which is typically in 1/R6. And this constant is related to the polarizability of the molecules. And if you go back to your electrostatic notebooks and you look at the dipolar interaction, for instance, there will be polarizability somewhere in the interaction. So it seems that the energy of interaction, let me call it alpha beta, or alpha is not a good choice, Ig between species I and species J, is something that is simply a constant times the polarizabilities, careful, alpha has another meaning now, of each individual monomeric or solvent molecule. Therefore, delta epsilon, which remember was epsilon pp plus epsilon ss over 2 minus epsilon sp. Well, it can be rewritten this way as k over 2 times alpha p squared plus alpha s squared minus 2 alpha s alpha p. So it's immediately clear that it is a positive quantity squared. Good. So delta epsilon is bigger than 0, which means that psi, the Flory parameter, is always bigger than 0. Of course, this is based on van der Waals interactions. If now I go to some biologically relevant interactions where you have really Clay-Serrure interactions with specific proteic-like interactions, this would not necessarily be true. In particular, in biology, you know that sometimes the best interaction is between opposite objects. Think about the basis in DNA. Someone likes really the other type of species. So it's a completely different type of interaction. But I'm talking about most interactions that are long-range interaction in cohesive materials and liquids. Okay, so van der Waals is the key example. So it's positive. It means that psi is always positive. Good. What is the minimum value of psi then? It's 0, and this is related to, it's equivalent to say the temperature goes to infinity, for instance. First possibility. Temperature goes to infinity, says that psi equals 0. Another strategy is to have delta epsilon, which is strictly 0. Or, which is equivalent to say that the polarizability of P is equal to the polarizability of S. So it says, basically the two objects are the same. Let me just extrapolate. I can write that. Well, in fact, what you're doing is that you are doing a chain of certain number of monomers that are connected, okay? I don't write all of them, but you have those monomers. And as a solvent, I take unconnected monomers, but of the same species. So if you want, this is polystyrene, PS, and this is styrene. Before polymerization. So in a sense, my solvent is the unconnected version of myself. And it is the best solvent. Why? Why? It's the ideal solvent. Because delta epsilon is equal to 0. which means that psi goes to 0, so V is maximal. V is the largest. So this is the solvent that would maximize the interaction, and thus that would maximize the swelling. So it's the solvent that would make sure that I'm really trying to extend. I'm happy in this world, and I would like to extend myself as much as I can because I'm really satisfied with this environment. Okay. We also call that, so it's a name, ideal solvent. We also call that the athermal solvent, because in this very specific situation, since psi equals 0, there is no more temperature dependency. That is here normally. There is only V equals AD. So you recover the fact that V is equal to AD, and so there is no temperature dependence. It's only the monomeric size to the power of the dimensionality of space. Okay. All right. So now we have started to make a connection with Flory's picture. Let me, so I don't have enough boards, so let me just erase the beginning of the lecture. And so we end up with P2, which is again RD minus 1, the Gaussian contribution. And now this renormalized version of the repulsion, but instead of AD, I keep V, the newly identified excluded volume. All right, so again, same story goes on. I'd like to make sure that I am at equilibrium, so I will maximize the probability or minimize the thermodynamic potential. This is a scaling symbol. So I have 3 terms times the 2 exponential. I don't write them anymore. RD minus 1 times this guy, so there will be n squared V over RD plus 1. That would be equal to the final term, which is RD minus 1, and R squared when it's derivated, it's only 1R, and A squared without any prefactors. And I removed already the exponentials. Okay, this is the minimization, saying that, sorry, it's not really clear what I wrote. I will do that, which implies that. So minimizing, extremalizing the probability gives me an identity between the 3 terms of the derivative. Okay, the following one. And again, this guy will be much larger than this one. Exactly the same argument as before. Just to be clear, let me just multiply everything by R2. So it's RD plus n squared V will be R2, so I have NA squared. And again, this term is RD over NA squared times R2. I should have done the opposite. All right. And this guy is expected if you start to swell. We are discussing the swelling situation where V is positive. This is becoming rapidly much larger than A squared. So this ratio is much larger than 1. And therefore, it will dominate rapidly this quantity. So you end up with a scaling law, which is RD plus 2 over NA squared. That scales like n squared V. Stated differently, this is n cubed VA squared. Or if you prefer to recast everything into proper, sorry for the typos, factors AD plus 2. So that now if I take the power 1 over D plus 2, I get NU, A, and a ratio to the power 1 over D plus 2. With nu, which is, as usual, 3 over D plus 2. So we recover the Flory exponent that is not a news, because already with the purely repulsive interaction, we got that fact. We recover AEC, which is not also a news, but now we have the proper renormalization factor that was missing in the previous step when we were not taking the interactions with solvents into account. But that now is here, and there is, since V is not necessarily equal to AD, there is a contribution here. So we can rewrite this as R goes like A and nu, and then you have this 1 minus 2 psi to the power 1 over t plus 2. Since V over AD is provided somewhere here. Here. So V over AD is 1 minus 2 psi. Okay. Where are we now? All right. So there is this new term here. Solvent and attractive interaction in general. Okay, what is the picture? You have the ideal random walk. Now you take into account the fact that you don't allow for self-crossing. So there is swelling. Nu becomes different than 1/2. First step. But you forgot solvent, so now you put solvent and all the interactions between all the monomers, and you end up with a renormalizing of that swelling. In fact, it is a reduction. This is smaller than unity. Okay, it's smaller than 1. So in a sense, you first swell thanks to the fact that you don't like to touch yourself, so you repel, but then you find yourself in a situation where the monomers of the chain, they are in contact with some solvent molecule. That they like those molecules, but they prefer much themselves. So they will then come back a bit by this attraction. So in fact, you always hear in laboratories that solvent makes you swell, makes you expand and dilute yourself into a solution. This is wrong. What makes you extend is the fact that you have repulsive barrier between yourself and yourself. And solvent is in fact doing the opposite. It's pulling you back because a general solvent is less good than yourself. You prefer to have a solvent of monomers rather than water or toluene or whatever. Of course, there is a particular case, which is the ideal solvent. And there you can really kill Xi to 0. And so you recover the pure extension. Okay? So be careful. Some people are conveying a wrong idea in the sense that the solvent makes you go well as a polymer chain inside the solvent. All right. What do we have to discuss now? Yes, I told you about Xi. So this was already question number 8, I guess. All right. Oh no, let me finish this. So we see that Xi is bigger than 0. We already discussed that. Now, what is the critical value of Xi, you could say? Is it obvious? Is there a special value of Xi?
1/2.
1/2.
Obviously. Xi 1/2 is a special value because then it will kill that term. Be careful. Don't say that it implies that R is 0. This is wrong. Because remember, here in this derivation, you had 3 terms. And you neglected that term under the consideration that this term was much larger because R was super large with respect to NA squared. Well, now if there is R which is going to 0, then you have to remember that you cannot neglect that term anymore. So keep this one and redo the calculation and you will see that there is no inconsistency. So I will not write that. I will just say that when Xi is equal to 1/2, then what you say is that rather than V is equal to 0. You can see that from the expression of Xi, which was somewhere. Okay, so V sorry, the expression of V was AD 1 minus 2 psi. So when psi equals 1/2, you have V equals 0. So there is a specific value of psi for which, despite the fact that your system has a certain size, the monomers are finite in space, well, everything is as if the interaction was going to 0. You're killing the interaction. And so what does it mean if you kill the interaction here? It means that you are left with an ideal random walk. If I put V equals 0, well, I can stop at P0. There is no P1, there is no P2. And therefore, you're back to this guy. With in particular the consequence that nu is equal to 1/2. So interestingly, when psi equals 1/2, you recover the Gaussian chain, the Gaussian statistics. And what psi equals 1/2 means, psi is Z connectivity of your space, delta epsilon, the comparison between segregation and mixture in unit of KT. So there is a specific value of temperature, for instance, for any solvent, where you can reach that situation, and thus where you can reach that situation. So remember at the beginning of the tutorial number 1, I told you, the ideal description, well, it's fake because we know that there are plenty of other problems, interaction, self-interaction, solvent, charges, whatever. But for any realistic situation with any solvent, there are some temperature playing, which allows you to come back to a real polymeric statistics that is described by free diffusion, Gaussian ideal diffusion. So this is interesting. It's a first indication that the ideal description is in fact useful. That's the first part. The second point I want to mention is that, of course, we have psi, which is equal to 1 minus, V, which is equal to 1 minus 2 psi. And we said that, well, first, psi equals 0, it's the minimum value, implies that V is simply the molecular volume. Good, it's the maximum value. Psi is now increasing, okay, from 0. And so there is at some point psi equals 1/2, where V equals 0. And now if I continue increasing psi, I will end up with negative V. So you will crossover or transition, in fact, from a situation where you have a positive interaction to a situation where you have a negative interaction. So I could write this as a unit of V if you want. The maximum value is given by AD. It's the monomeric volume. So you start from that, is the ideal situation. Then by increasing C, you end up in a situation where you have a chain which is nicely swollen inside the solvent, to a situation where if V is negative, you can do it, it will collapse fully. You have a term of entropic elasticity that pulls you down, and you have an interaction that also pulls you down. So I mean, there is no balance anymore, everything collapses, and now you have really a stack assembly of molecules. I mean, really everything is precipitating, if you wish. And the transition is for V equals 0 here. In terms of exponent, this is nu equals 3 over d plus 2, Flory-like. This is what is nu in a compact situation according to you? What is the relation between number and volume? Really, I have a packing of spheres now in d dimension. So what is the exponent?
N to the power 1/3.
N?
1 over d.
Yes, correct. in 3D, for instance, it would be 1/3, meaning that R goes like n1/3 A. Stated differently, R3 goes like N, if I forget about units. The volume is proportional to the number of objects. Each time I add an object, I must add its volume. So it's really like a dense packing. So I will cross over or transition between the two at a value, which is a critical value, which is 1/2. So in a sense, this V, remember, it depends on temperature because Xi depends on temperature here. So I take a certain solvent and then I change the temperature, and by changing the temperature, I will transition from a certain statistics to a completely different one. So it's really a phase transition in a proper sense, and there is a critical exponent at the critical point, which is 1/2. Okay. More practically, by changing the temperature in a solvent, you might play on precipitation or solvatation, okay, which was known for most of you. Perfect. Final point, what is the critical temperature? We need to estimate the critical temperature. Well, this is coming from this simple identity, and Xi is equal to Z delta epsilon over KT star, which is 1/2. So it says that T star is equal to 2Z delta epsilon. Okay. And so during the glorious age of polymer physics, this transition was checked and this critical temperature was found. And now in organic chemistry laboratories and in physicochemistry laboratories, people know the temperature for a given polymer and a given solvent, and then play above or below depending on what they want. All right, so we will stop here for that discussions. You saw that we were remaining at the level of scalings on all quantities. We wanted to have an understanding of the main features. We didn't want to go into the details of the interaction description. However, there are methods that are called self-consistent field methods that are much more robust, and we will revisit some of those in later tutorials. But for now, you are starting to create your own picture of what is a realistic polymer statistic description. Do we have any question? General or specific? Okay, so otherwise, feel free to contact me by email with private questions, and I will record. I mean, I will save this video and put it in the common Dropbox. I hope everyone has access. Again, otherwise, just contact me, and I will make sure you have access. And with that, I wish you a very good weekend and a very good week, and see you next week. Thank you.
Thank you. Goodbye.
Goodbye.
Thank you.
Bye.
Goodbye.